right, let's do this. So, liquids. By the way, happy Earth Day. So we are looking at this vapor pressure curve, and so we find 40 degrees, which is about here, and where we hit this curve, this one's sitting pretty much, so for the CH3NO2, it's 100 millimeters of mercury. Now, question, Christian asked me a really good question during office hours. I did not mention this, but millimeters of mercury are the same thing as torr. The chart that was in our notes was in torr. And so if you figured that out, that's great. Next week, we'll be doing gas laws, and that will, those two units are interchangeable. And then you keep going up. And this is kind of halfway between the 60, 650-ish. And you do want to put a unit with it, so torr, millimeters of mercury. The type of intermolecular force, so CS2 is linear. It's going to be like CO2 was, so it is nonpolar. So London or induced dipole. And then the other one, the hydrogens again are on the carbon. Nitrogen and oxygen are going to pull, so it is polar. So the type is a dipole. Normal boiling point means at 760 torr or millimeter mercury. So we would just find 760 on here, and we would come across, it's where our graph ended apparently. So 95-ish degrees Celsius. Oh, for this one, and for this one, it's looking like it's like 48-ish degrees Celsius from the graph. Again, if you said 47, if you said 49, we're in the ballpark. So I'm just looking that we're all in a similar ballpark. Vapor pressure of 600 for the CS2 we'd come across, and it's, you know, if you said it's at 40, that's fine. 38 degrees. My line is not a perfectly straight line, so we're in that same ballpark. And 60 millimeters of mercury would be way down here, so probably around 30 to 32-ish degrees Celsius. All right, so just reading the graph. These are questions that I actually enjoy because they're like puzzles. So you have A, B, and C, and so the vapor pressure of A is less than the vapor pressure of B, which means that A has stronger intermolecular forces. And that C has the highest boiling point. So for IMF, C is the strongest because it has the highest boiling point. So strongest IMF. B would be the weakest because it had the highest vapor pressure. And then A was in the middle. So questions with that. And by the way, so my sense of humor is bronze, silver, gold. That's like what they give at the Olympics. So the highest one was the gold. Somebody last year didn't understand my sense of humor, so. In your own words, viscosity is stickiness or resistance to flow. Anybody else have something? Like way of saying that? Temperature absolutely does. If you increase the temperature, you're going to decrease the viscosity. The reason for that, as you increase the temperature, you increase the jiggles, the kinetic energy. So if you have more kinetic energy and they're jiggling, they're not going to get stuck to each other. So like honey, if you get real honey, that you often have to heat it up to pour it out. And then we have these chemicals, and wants to know which one is going to be the most viscous and why, and it's going to be our last one. So see all these OHs in there? This guy has 3 H bonds. This one had only 2 H bonds. 3 is always better than 2. And this one had only one H bond. So that one had 3 H bonds. And which one's going to be the most volatile? So I should have left water out of it. Water is going to be like in between probably the ethylene glycol and the ethanol. So it's probably going to fall in here because it does have 2 H bond possibilities because of the OH. You have an H on each side of it. And then these carbons interfere with the H bonding because they give some non-polarity in there. So the most volatility is ease to evaporate, how fast it evaporates. So again, the best example is octane, that when you put gasoline in your car, it evaporates really fast. Or if you spill something, alcohol evaporates really fast. So people, hand sanitizers right now are really high in a lot of alcohol, and so they evaporate. So the most volatile is going to be the weakest, and that would be the ethanol because it had only one H bond. I would not ask you, yeah, the water one's a tough one. But the ethanol is more volatile than the water just because of those carbons give it a non-polarity. All right, the true statements. As you increase temperature, again, you're going to increase the kinetic energy or the jiggles, which is going to decrease the intermolecular forces. It's going to make everything come apart. And so the surface tension would decrease. So A is wrong. B is good. B is correct. So same thing, it's going to be jiggling, and so it's going to escape the liquid. And that is what vapor pressure is. It's when it escapes the liquid. All right. C is what this curve is showing and that I talked about. So as you drop the vapor pressure, so I talked about with elevation, but as you drop the atmospheric pressure, the vapor pressure, the boiling point decreases. So that is true. So C curve, we'll just say. And then D doesn't matter at all. So it's saying you have like a big pot or a little pot. And so the surface area of the container has absolutely no effect on the surface tension. The surface tension is determined by what the molecule is. So what type of intermolecular force it is. Any questions on that page? It was pretty fast. Motivated. All right. So I apologize. I thought there were number answers on here, and when I posted it, I didn't realize until I looked at the first person who submitted it, and I'm like, oh, I don't know if they had the answer right. So the next study set for next week, there are answers there, so you can see how you're doing along the way. But that was the answers for those 2 questions. On the worksheet, there's one. You can always stay after and have me check it. So the curve, I'm going to draw it on this one, the full thing. It is a staircase. And my pen's going to run out. So you have just 2 flat lines. The lower flat line is the melting point, and the upper one is going to be our boiling point. And the upper one corresponds to delta H of vaporization. The lower one is delta H of fusion. So then you have these 3 diagonal lines, and they correspond to being the solid, the liquid, and the gas. So when you make your drawing, that's really all you have to have labeled. Your flat line should be corresponding to the boiling point and melting point. And so like on this one, I gave you a boiling point. You can't fill in the lower half because I didn't give you any numbers, but since I'm down on this one, we'll just do this one. If you want to add numbers, you can. There's what I see is half the students, you do need at least a symbol there for each one. And the liquid is 117.2 joules. In this one, they use moles instead of grams. And the gas is the 72.3. All right, so we're actually only using this upper half of the graph. We're not going to use this part down here, but just to see what the full graph would look like. And then, so it says draw and label the diagram. Is there any questions about the diagram? And then we're going to have 20 grams, so negative 40 degrees must be somewhere here, and positive 40 would be up here. So we're going to go through liquid. We're going to go through 3 steps. Just label your steps, what they are. That's the key. That's really our mantra tonight, is labeling. We're going to be doing a lot of math tonight with geometry. And as long as you label and state the formulas, students end up doing really well with it. So we're here in the liquid. Our boiling point again was given as negative 29.8. So for the liquid, this is where we're going to do the mass. They always involve the mass. And in fact, I realized after I did this in class and showed you how to do it, you can always start with the mass for all 3 steps. And I'm going to do that actually today, just to show you. And then you can bring in the numbers. So for the liquid, we have the 117.2 joules per mole degree Celsius. So we're going to have to change our grams to moles for all of them because they have moles there. Did it give us? Oh, did somebody figure out what our molar mass is?
It was 120.9.
121, would you say? Oh, 120.9. Yeah. So they're all going to, so I'm going to change this step, sorry. We have to get to moles because they had this mole unit that we're going to have to get to. So 1 mole on top over, we say it's around 121, 120.9. So our unit cancels, and then we'll bring in that number. Usually these diagonal lines are joules per gram degree Celsius, so we can ignore the mole. So this is joules per mole degree Celsius. So we just really, what you're trying to do is to get your units to cancel out. So that cancels out the gram, cancels out the mole. We have to get rid of the degree Celsius. So the key is that this is a change in temperature. So from here, which was negative 40, to our boiling point, which was negative 29.8. So a 10.2 degree change. So when you do the liquid, the temperature change is just the change as the liquid, which will be the 10.2 degrees Celsius. And I think, yeah, so there's a reason my answer is negative. It's saying that we're cooling down, so I showed my arrows backwards. I apologize. So you're actually going backwards on this graph, which is going to give you a negative. All these numbers are going to come out negative. And how it would work is your temperature change is final minus initial. So you would technically say negative 40 minus negative 29. So it's a negative 10.2 degrees Celsius change. I always go to kilojoules. So 1,000 joules to 1 kilojoule. The order that you do these steps in doesn't matter. It does matter that you have the correct thing on top and bottom. So for the second step, if you start with the 20 grams, we have to get to moles. So again, around 121 grams per mole, because it's the compound was given here, carbon, dichlorine, and difluorine. And a reminder, actually, Tuesdays are class presentations. So you all told me when you were presenting, there are more people in the evening one. So if somebody was able to switch, you can let me know, or you can shoot me an email, or we'll just go with how the split happened. So 3 to 5 or 6 to 8, is that what we said? Okay. We want to bring in this
Wait,
number. Go ahead.
Is it 2 to 4 or 3 to 5?
Does anybody remember? I can't find my sheet.
I thought it was 2 to 4.
Is it 2
I
to 4?
heard 2 to 4.
Okay, 2 to 4. Oh yeah, because I do have something at 4 o'clock. That's right. It's 2 to 4. Damon, were you able to switch, or you're not sure yet?
I'll say yes for now. We'll just go ahead. It should be okay. 95%
Okay.
positive.
If it's not, then just I'll know that you're coming to the later one. If you're not
I'll
there
know.
at 2
I'll
o'clock.
know by Monday. It just
Okay.
depends on my work schedule.
Okay. Thank you. So yeah, it's 2 to 4 or 6 to 8. Thank you. And you guys all know how to share your screen. So then kilojoules, this is already in kilojoules. So we're good. That one we're done. We would just punch in our calculator. You can find each answer, and then we're going to add them up. And then our last step, again, on this one, we have to go to moles because they gave the unit in a funky unit, the 72.3 joule per mole degree Celsius. So we need our mole to cancel. And then again, this is our change in temperature, which is going to be from our 40 degrees to the negative 29. So this is negative 69.8 degrees Celsius. I need to be clear on this also. This becomes a negative value. So if you guys remember when we did heat, if it's positive going in this direction, then it's going to be negative because we're going backwards on this curve. So all of your answers are going to be negative. And so that's why my final answer is negative. Or you can just do it in the positive direction, like we always do, and then change your answer to a negative. But the answer is around negative 4.8 kilojoules. Yeah. All right, for the top one, all we're going to deal with is the solid and the delta H of fusion. We don't actually, we can show the full graph, but we don't need the liquid, the delta H of vap, or the gas. Those aren't needed. And so you can ignore them. The solid, so we're just going to have those 2 steps. You didn't, on the worksheet, you have to draw like the full picture and label. And then I know you don't need all 5 steps. I think you need to do 3 steps. For the solid, we're going to have 3.14159 grams. And it is silver. And it tells us it's that number 0.234 joules per gram degree Celsius. And then the temperature is our change in temperature. So it just gave us 2 temperatures. So the difference in those is what, 941 degrees Celsius. And then we would add it to the heat of fusion. So 3.14159 grams times our number there for the heat of fusion, 11.3 kilojoules per mole. And so if you write it out like that, you should hopefully see, wait, my units are not going to cancel. So to get our mole and gram to cancel, we need the periodic table. It is silver. And so silver on the periodic table is 107.9 grams to 1 mole. And you would punch these in. Oh, you got to have the same unit. So this is kilojoules. So make sure you change the one that's joules to kilojoules. So as long as you write your units, it's all just units. And as long as you label what your steps are, so solid and heat of fusion, and then this one was liquid, that. So you should get around 1.02 kilojoules or 1,020 joules. Questions? All right, you can stop.